Hello everyone. Today we are getting into the world of concurrent programming with a very classic problem, which is also very famous. It's the dining philosopher problem. And we are going to see how could we solve this with the Go language. Now let me introduce you the dining philosopher problem. The problems involve a situation that there are 5 philosophers sitting around a circle table while they only do 2 things, think and eat. There are only 5 chopsticks available on the table. Each one is between each 2 philosophers. If a philosopher will need to eat, he needs both chopsticks on the both sides of him. Our goal of solving this problem is that we need to allow all the philosophers could eat and think and avoiding some situation like starvation or deadlock. As it mentioned before, we decide to choose the Go language to solving this problem. Why do we choose that? The answer is because Go language offers a lot of powerful and easy to use features for concurrent programming. To be specific, is mainly these 5. The first one is the Go routines, which is a very lightweight series for execution that managed by the Go runtimes. We can use it in a very convenient way like this. This allows the concurrent execution of function in a convenient way. The next one is the structured channel, which could send and receive values between different threads and help us to synchronize and communicate between different go-to times safely and easily. The third thing I would like to introduce is the select structure. It actually works together with the channels I just said. It has a function that's similar to switch structure in some other languages, but the difference is that each case of such select structure has to be a channel. It operates as that provides another way to handle that multi-channel situation. Each time a channel of the case is ready, then we will run the operator under this situation. The mutex is the next thing I would like to introduce, which provides another synchronized tool that could help you use to control the access of the thread resources between different threads. It actually works like a mutual exclusion lock. Similar to other things, you could run it in a very convenient way by import the Cynic packages and create a mutex lock. Then just use it in your function in a very easy way. Just lock or unlock it as you like. As this mentioned here is we use to the package of Cynic. So I could introduce the very powerful package Cynic to you. It provides most of the basic synchronization operator we need to use. The mutex or read-write mutex, it just has been explained before. And the once function is to ensure that a function would be only called once, even there are multiple Go routines as uses. It will be useful to create some new variable. The wait group function plays a role that allows a Go routine to wait for another group of Go routines for completion. The last thing I would like to introduce is the Cynic atomic package, which is quite different. It has a limited usage of some kind of data structure, and it do not have a lot of operators. It could only do something like add or subtract or load or store. But the biggest greatest is that the first, it has a very high performance. It could be like 15% faster than other packages. Second, it could be used to safely modify some variable or to modify the threads with no need to use any locks because it's a package that operates directly on CPU. So it's avoiding a lot of error situation and could remain the safety of our data as well. This is the reason why such a package is useful and I would like to introduce to you. In conclusion, Go language has features like simplicity, lightweight concurrency with the Go routines, and building support for channels and switch and high-performance operator with the help of package Scenic and Scenic Atomic. All this make it a very attractive option for concurrent programming. Later, my teammate Yifei would introduce you how we actually use this for solving this problem. Thank you.
So, how can Go languages help us in our code? I think it has four aspects like Go routines, channels, struct and methods, and select statement. For this one, I think our method just use structs with channels and use Go routines in main function and use syntax of the select statement. And let's see our codes. Here, let's just first see the left side of that. Here's a whole bunch of that, just the local function. All function has a local, which is a basic and important part of that. And the local controller, the controller to control the two sides of chopsticks, which has a channel with a capacity of the empty struct. And also, and also for the new local controller, just create a new one. And for lock and unlock, these two functions just use to replace the semaphores and condition variables, because the locker can have same functionality, like inside the lock, we just add the empty structure inside channel, and unlock we just extract this content from the channel. So for the function is lock, we just check just to check if there is something inside the channel. If there is, return true, and otherwise return false. And this is an important function for our next code. And on the right hand side of that, we create a constant non-philosophers, which means the number of philosophers on the table. Now it's 5, because it's classical number here. You can change this if you want for testing. And the philosopher and the philosopher creator is, I think, it's similar to the local controller. They both has the construct functions. And for the philosopher, I think we have the attribute of ID, left and right chop, which belong to local controller. And this is just the definition. This page is about pick up chopstick. For this part, we have some refinement during coding. Like this is our previous graph. What this algorithm here is just of like each philosopher takes left chopstick, and from so on, and the last one, the last philosopher takes the right chopstick. I think this algorithm will prevent prevent this code from the lock. But the problem is that there is a long path here. I think this is not very efficient. And to improve the efficiency, we just moved here the above graph. Like we just determined that the even ID philosopher takes the left hand side chopstick, and odd ID philosopher just take right hand side, just like here. Like this part code. Let's talk about this content, and here you just talk about if you take left hand side chopstick, you just try to take the other side, and this is here the same. And if philosopher take both chopstick, they can start eating. Yeah, I think this is main logic here. And here, you just put down the chopsticks, unlock and unlock right and left, and this is quite simple. For it, I think first first alongside just randomly generate philosopher, which can help prevent them from starving. And also for this for loop, we just check if they can pick up those chopsticks. If so, just start eating, and if finished, just put down the chopsticks and the others, and otherwise just thinking. This is quite simple, and for the main function, I think we just for testing. Here is just guaranteed chopsticks has the same number as philosophers, and this create a this function create a philosophers outside. Here we just start eating and keep running. If our function cannot we're not facing the problem of deadlock, we are forever running for that.
So here's our code for the program, and just as I mentioned before, now we're gonna test how this works. I need to mention that now we said that there are 5 philosophers thinking together. It could be changed to any number we like. So from the testing result, we can see that we have output all the things that philosophers would do. That a philosopher first starts try to pick both chopsticks, and then if they could have both chopsticks, they start eating. And when they have finished eating, they're gonna put down both chopsticks and start thinking. This could be one iteration or one loop for the philosophers. And from this we can see the philosopher 4 first get both chopsticks and start eating, same as the philosopher 1. And this could show that the eating together could be they have the concurrent ability of eating, and so as we can check that the philosopher 1 and 2, the philosopher 0, the philosopher 3, the philosopher 4. Philosopher 4 is eating. So as you can see here, all the philosopher has the chance to eat. If they got both chopsticks, then they could eat. So this could prove that we have avoiding the problem of starvation. And also there's no stop with error and no exit for some reasons. And this could prove that we have no deadlock in our algorithms. And also sometimes if some philosopher will try to get the chopsticks while such chopsticks has been used for some other people, for some other philosophers, then they cannot pick them up. And in this situation, he needs to put the one he has picked back. It also follows what we would like to let the algorithm run. So this could show the correctness and the performance of our algorithm. Also, if you like, you can change this to some other number like 10, like 19. We can see that our algorithm still runs very well, and all the philosophers are eating and thinking in a right way. So I think this demonstration could prove that our solution to the dynamic philosopher problem by the Go language has correctness, and it has achieved what we want for our solution. That's all for our videos. Thank you so much.